turn off the lights. No, I mean it. Somebody go find the switch. I want to start in the dark. I want you sitting here in the actual stuff I'm about to talk about, because here's what I want to ask you before your eyes adjust, before you start making sense of shapes and shadows. What is darkness exactly? You've been inside it your whole life. You were born into it. You sleep in it. When you were small and afraid of it, nobody thought to tell you what it actually was. They just told you it wasn't anything. They said there's nothing there. And that, my friends, is the first lie we tell children about the universe. Because darkness is not nothing. Darkness is not the absence of anything. Darkness is not even technically what you think it is when you're sitting in a dim room and you say to yourself, it's dark in here. The thing you are experiencing right now, or the thing you experience at midnight or in a cave or under your blanket as a child, is one of the most spectacular, strange, and frankly underappreciated phenomena in all of physics, and nobody talks about it properly. So let's talk about it properly. Let me start somewhere obvious, somewhere everybody agrees, somewhere even your grandmother agrees. Light comes from sources. The sun, a candle, a bulb. Light is produced. Light travels, light hits your eye, and when there's no light hitting your eye, you see darkness. Simple, clean. Now everybody relax, because that's the last simple thing I'm going to say for a while. Here's where it gets interesting. When we talk about light, real light, not the everyday lamp in your hallway, we are talking about electromagnetic radiation, a wave, an oscillating electric field married to an oscillating magnetic field, rolling through space at 299,792 kilometers per second, which is a number so large that if you tried to drive your car at that speed, you would circumnavigate the Earth 7.5 times in the time it takes your heart to beat once. Light is not a gentle little particle that politely illuminates things. Light is a violent, beautiful, quantized wave particle that is fundamentally woven into the structure of electric charge itself. Every time an electron changes its energy, jumps from one state to another in an atom, accelerates in a wire, wiggles in a fire, it emits light. The universe is lit by the restlessness of electrons. Now, if light is this frantic, constant, perpetually being produced thing, then why is anywhere dark? Why isn't everything illuminated all the time? And the answer to that is not because light runs out. Light does not run out. Light travels until it hits something and gets absorbed. So darkness isn't the absence of light production somewhere. Darkness is the absence of light arriving at your eye. These two things sound the same, but they are not. And the difference between them is the beginning of something deep. Let me tell you about a man named Wilhelm Wien. This is a real story about a real human being who sat down in the 1890s and tried to figure out why hot things glow the colors they glow. You know this. You heat up a poker in a fire, it turns red, then orange. Then if you get it hot enough, it goes white. Wien wanted to understand that. He sat there in an era when nobody yet knew quantum mechanics. Nobody knew what an atom really was. Nobody had discovered the electron's charge with any precision. And he figured out that the color of light emitted by a hot object depends on its temperature. Cooler objects put out more red. Hotter objects shift toward blue. Wien made an empirical law. He measured it. It worked beautifully at some temperatures. And then at low frequencies, it broke. It didn't just deviate. It exploded into nonsense. It predicted that a room temperature object should be blasting out infinite amounts of radiation at low frequencies. This became known as the ultraviolet catastrophe, which is a wonderful name for a crisis in physics, infinite energy coming from a cool metal box. Something was profoundly wrong. The man who fixed it was Max Planck, and he fixed it famously by making an assumption that he himself called an act of desperation. He said, what if energy is not continuous? What if energy can only be emitted in discrete chunks? What if there is a smallest unit of energy, a quantum? He introduced this number now called Planck's constant, which is a vanishingly small number, 6.626 times 10 to the negative 34 joule seconds. And he showed that if you assume light comes in packets, not streams, the catastrophe goes away. The curve matches experiment perfectly. Planck did not know why energy was quantized. He just forced it to be because the math required it and hoped somebody would explain it later. Einstein explained part of it in 1905 when he used the same quantum idea to explain the photoelectric effect and won the Nobel Prize for it, and quantum mechanics eventually explained the rest. What does any of this have to do with darkness? Stay with me. I'm about to connect the threads. Here is what quantum mechanics tells us about that room you're sitting in. Every object that has a temperature, any temperature above absolute zero, is radiating electromagnetic energy. Your chair is radiating. The walls are radiating. You are radiating. Right now, your body is emitting electromagnetic radiation at a peak frequency determined by your temperature. Your skin is about 305 Kelvin, which means you are glowing, not in visible light, not in the frequencies that hit your eyes and register as brightness, but in infrared, in the electromagnetic spectrum. You are glowing in a frequency that pit vipers can see and that thermal cameras record with perfect clarity. You are never dark to a snake. You are never dark to a satellite equipped with the right detector. Darkness, as it turns out, is a statement about which detector you happen to be equipped with. Your eye evolved to detect a specific narrow band of electromagnetic radiation. Everything outside that band is invisible to you, which means everything outside that band looks like darkness, but the radiation is still there, still screaming, still filling the room. Sit with that for a moment. The darkness in your bedroom at night is not emptiness. It is a room full of infrared radiation from you, from your walls, from your pillow. It is a room threaded through by radio waves from transmitters hundreds of kilometers away. It is a room penetrated constantly by high-energy cosmic rays from supernova that exploded millions of years before human beings existed. It is a room bathed every single moment in the cosmic microwave background radiation, the afterglow of the Big Bang itself, the oldest light in the universe, now stretched by the expansion of space to microwave frequencies, still arriving, still present in your bedroom, in the cave, in the darkest place you have ever been. You are never in the absence of electromagnetic radiation. You are only ever in the absence of the narrow sliver your eye can see. That word visible, that word should embarrass us. The visible spectrum, what we mean by visible, is visible to this particular evolutionary accident called the human eye. That's it. That is not a definition of light. It is a definition of our limitations. The full electromagnetic spectrum spans from radio waves with wavelengths bigger than a football stadium down to gamma rays with wavelengths smaller than an atomic nucleus. And the piece our eyes respond to is a thin sliver, roughly from 380 to 700 nanometers in wavelength. If the electromagnetic spectrum were a grand piano that stretched from one side of this hall to the other, the range you can see would be one key. One single key in the middle of a concertgram, and you call the rest of the piano silence, you call it darkness. But the piano is playing constantly, has been playing for 13.8 billion years, and you are just a creature who can only hear one note. Now here is a question that seems philosophical, but is actually physics. What would it feel like to see all of it? I don't mean to look at a thermal image or put on special goggles. I mean, what is the difference between seeing and not seeing a specific frequency of electromagnetic radiation? What happens in your eye when light enters it? Because if you understand that, you understand something remarkable about what darkness really is. Your eye contains photoreceptors, rods and cones, and inside those photoreceptors is a molecule called retinol, which is a form of vitamin A that has been twisted by evolution into a very particular shape. When a photon, a single quantum of light, hits that molecule, it changes shape. Literally, it flips from what chemists call the cis form to the trans form, like a little door swinging open. That shape change triggers a cascade. The retinol detaches from its protein. The protein activates another molecule. That molecule activates another. And eventually an electrical signal goes roaring up your optic nerve to your brain. One photon, one quantum of light. That is all it takes to trigger the whole chain. 1. The human eye, adapted to darkness, can detect a single photon. We know this. It has been measured. You are a single photon detector under ideal conditions. That is extraordinary. You are running right now a biological quantum detector in your skull. But here's the catch. Retinal only flips when the photon has energy in a specific range. Infrared photons don't have enough energy to do it. Ultraviolet photons have too much and damage the detector. Your window is narrow, not because photons outside that range don't exist, but because your detector doesn't respond to them. Darkness, then, is not a property of the universe. Darkness is a property of the eye. Darkness is the universe telling you something is there that you are not equipped to see. Darkness is not a wall. Darkness is a mirror. It shows you the limits of your own perception, not the limits of what is actually present. Let me tell you the strangest thing I know about darkness, and I want you to stay with me because this is the part where it gets genuinely, deeply strange. We think of space, outer space, the void between the stars, as the darkest thing there is. You've seen the pictures. Black, empty. The stars are these little bright punctures in an enormous curtain of black. And it seems obvious, doesn't it? Space is dark because space is empty. There's nothing out there to make light. So of course it's black. But wait, this doesn't actually make sense. The night sky has been a problem for physicists, a genuine unresolved paradox, for centuries. In 1823, a German astronomer named Heinrich Olbers asked what seems like a childishly simple question. If the universe is infinite and infinitely old, and stars are distributed throughout it, then why is the night sky dark? Think about it carefully. If you look in any direction in an infinite universe full of stars, you should eventually be looking at a star. The further away, the dimmer. But in an infinite universe, there are infinitely more distant stars, and the math of it works out to say every line of sight ends at a star, which means the whole sky should blaze with the light of infinite stars. The whole sky should be as bright as the surface of the sun. At night, always, the entire sky, brighter than noon, and it isn't. It's dark. So what is going on? This is called Olbers Paradox, and it bothered people for a long time, and the answer to it is one of the most beautiful things in all of physics. The sky is dark at night because the universe is not infinitely old. The universe had a beginning. Light from very distant stars has not had time to reach us yet. We cannot see infinitely far because the universe has only been around for 13.8 billion years, and light takes time to travel. There is a horizon beyond which we cannot see, and the observable universe has an edge, not because space ends there, but because time began there. The darkness between the stars is not emptiness. It is the edge of time. The darkness is where the light hasn't arrived yet. You're looking at the future, or rather you're looking at the place where the past hasn't reached you. And on top of that, the universe is expanding. Light from very distant galaxies is being stretched as it travels, its wavelength stretched longer and longer by the expansion of space itself until it drops out of the visible range entirely into infrared, into microwave, into radio. Stars don't just recede past our horizon. Their light literally fades from view because the universe is pulling it down through the spectrum into frequencies we can't see. So part of the darkness of the night sky is stars whose light we've caught, but whose light has been redshifted into invisibility. They were there. The photons arrived. We just couldn't see them with these eyes. Darkness again is a limitation, not an absence. I want to go one level deeper now, because the real strangeness is not in outer space. It's in here. It's in the structure of matter itself, in what happens when light enters a material and is absorbed. When a photon of the right energy hits a material, say a black surface, what happens? The photon is absorbed. And what does that mean exactly, absorbed? The photon ceases to exist. It doesn't bounce back. It doesn't pass through. It gives its energy to the electrons in the material, which then release that energy as heat, as infrared radiation, which disappears from our sight. So when you look at something black and it looks dark to you, what you are seeing is not the absence of light. You are seeing an object that is converting visible light into invisible light. It takes in photons at frequencies you can detect and re-emits them at frequencies you can't. A black object is a transducer. It converts visible energy into invisible energy, and you call it dark. It's not dark. It's just radiating outside your detection range. Every black thing you've ever seen is quietly glowing. You've just never been able to see it. The perfect absorber, something that absorbs 100% of all incident radiation across all frequencies, is called a blackbody, and a perfect blackbody is simultaneously the darkest object you can imagine, and at any temperature above 0 Kelvin, also a radiator of electromagnetic energy. A perfect absorber is also a perfect emitter. You cannot have one without the other. Thermodynamics forbids it, so the darkest imaginable object is still emitting, still radiating, still in some sense glowing. The universe will not permit the truly dark. Even in deepest space, far from any star, there is the cosmic microwave background at 2.7 Kelvin. Even a perfect blackbody drifting through intergalactic space is bathed in this ancient radiation, absorbing it, re-emitting it. The temperature of empty space is not zero. It is 2.7 Kelvin. The universe has a floor. It is not zero. It is the temperature of leftover light from the beginning of time. And then there's something else, something I find genuinely unsettling, and I don't use that word lightly because I've spent my career looking at things that would unsettle most people and finding them beautiful. I find this one beautiful and unsettling in equal measure. In quantum field theory, which is the deepest description we have of how the universe works, the theory that predicts quantities to 12 decimal places of accuracy and has never been wrong in any experiment we've done. In that theory, the vacuum is not empty. What does that mean? It means that space itself, even in the absence of any particles, any photons, any matter, even in the thing we used to call the void, is seething with fluctuations. Virtual particle pairs are continuously popping into and out of existence. They borrow energy from the vacuum, exist for a time so brief that the uncertainty principle permits it, and then annihilate, giving the energy back. You cannot catch them. You cannot use them. But they are real. They have measurable effects. The Casimir effect, which has been experimentally confirmed, is caused by these vacuum fluctuations. If you take two uncharged metal plates and place them very close together in what we think of as vacuum, they attract each other. Why? Because the virtual particle modes that can exist between the plates are fewer than the modes outside, and the outside pushes in. The void pushing two metal plates together. We measured this. It's not a hypothesis, it's a measured result. And Hawking radiation, the most famous prediction of Stephen Hawking, who was one of the finest minds the last century produced, Hawking radiation is based on vacuum fluctuations at the edge of a black hole. When a virtual particle pair appears at the event horizon, sometimes one falls in and one escapes. The one that escapes carries real energy away from the black hole, which means the black hole slowly, over astronomical timescales, loses mass. Even a black hole, the darkest, most light-absorbing thing in the known universe, is not truly dark. It is, in theory, glowing with a dim radiation born of quantum uncertainty. The darkest thing in the universe is still emitting. The void is not empty. Now let me take a breath because I've gone very deep very fast, and I want to tell you something important about this kind of science. When physicists first worked out the energy density of the vacuum, the energy that should be present in empty space due to quantum fluctuations, and when cosmologists measured the actual energy density of empty space from astronomical observations, the two numbers disagreed, not by a little, by a factor of roughly 10 to the power of 120. That is a 1 followed by 120 zeros. This is, without exaggeration, the largest discrepancy between a theoretical prediction and an experimental measurement in the history of science. It is called the cosmological constant problem. And nobody knows the answer. This is not a solved problem. This is an open wound in the middle of physics. Two of our best theories, quantum field theory and general relativity, give answers about the energy of the vacuum that are almost incomprehensibly different. The darkness of space, the energy in what we call nothing. This is one of the deepest unsolved mysteries we have. I want to linger on that for a moment because people sometimes think that unknown means unimportant or that scientists are embarrassed by what they don't know. We are not. The unknown is where the joy is. If I already knew everything about darkness, I would have nothing to talk to you about, and more importantly, I'd have nothing left to figure out. The mystery of the vacuum, energy, is not a failure, it's a frontier. And frontiers are where discoveries live. The history of science is a history of people staring at something they didn't understand and saying, I don't know yet. Let me try to find out. That's not a weakness. That is the entire method. And speaking of frontiers, there's one more piece of this story that I cannot leave out because it connects the darkness of the night sky to something even stranger than anything I've said so far. In 1998, two groups of astronomers, Saul Perlmutter's team and Brian Schmidt's team, led by observations from Adam Rees, were measuring distant type Ia supernovae, which are useful to astronomers because they always explode with roughly the same intrinsic brightness, making them reliable distance markers. These teams expected to find that the expansion of the universe was slowing down. Gravity pulls things together. All the matter in the universe should be gradually decelerating the expansion. They were measuring by how much. Instead, they found it was speeding up. The universe is not just expanding, it is expanding faster and faster. Something is pushing space apart, and not just pushing it, but accelerating the push. We have absolutely no idea what this is. We call it dark energy, which is a wonderful name because it tells you almost nothing. It's dark because we can't see it. It's energy because it has effects. Beyond that, we genuinely don't know what it is. It constitutes roughly 68% of the total energy content of the universe. The majority of the universe, in terms of energy, is something we cannot see, cannot directly detect, and cannot explain. And there's another 27% that's dark matter. Matter that doesn't interact with light at all, that we can only detect by its gravitational effects on things we can see. Add those up. Dark energy plus dark matter, the things we can't see, make up roughly 95% of everything. The matter you can see, the stars and galaxies and planets and people, the entire visible universe, everything in every telescope, everything you've ever looked at, is 5% of what's out there. 95% of the universe is dark, not because it's absent, because it's invisible to us. Because our instruments, like our eyes, are limited, because we are sitting in a universe that is mostly, by any measure we care to apply, operating entirely outside the range of our ability to see it. And when you look at the night sky and you see the darkness between the stars and you think that's empty, that's nothing, you are looking directly at the 95%. You are looking at the dark matter through which galaxies swim, at the dark energy that is pulling space apart, at the quantum vacuum seething with virtual fluctuations, at the cosmic microwave background arriving from the first 380,000 years after the Big Bang. The darkness is not empty. The darkness is almost everything. This changes how you should feel about the dark, not frightened, not comforted. Something more interesting than both, astonished. Astonished that this thing you've walked through your whole life, this thing you described as nothing there, is the majority of the universe, is the birth cry of time itself, stretched into microwaves, is vacuum energy that tears apart our best theories, is dark matter halos surrounding every galaxy, is dark energy accelerating the cosmos toward a future so vast that eventually every other galaxy will disappear from our observable horizon. The darkness is not a backdrop, it is the main event. We are the footnote. I want to come back to something small, something you can do tonight if you want to. Go into a room and turn off the light. Don't be afraid. Don't immediately reach for your phone. Just sit in it. Let your eyes adjust, which they will, because your rods are extraordinarily sensitive, and they will begin picking up the photons that are still there, the street light through the curtain, the starlight, the reflected ambient glow. And then think about what you now know. You're sitting in infrared radiation from your own body. You're bathed in radio waves from transmitters on the other side of the planet. You're receiving right now the oldest light in the universe, the microwave afterglow of the Big Bang arriving from every direction at once. Virtual particles are flickering in and out of existence in the very space between your fingers. Dark matter is flowing through you, through your body, through the walls, through the earth, unimpeded, undetected, at velocities of hundreds of kilometers per second, and dark energy is gently, relentlessly pushing the fabric of space apart around you, in you, between the atoms of your hand. You are not sitting in nothing, you are sitting in almost everything. I've been thinking, while I've been standing here, about why this matters, not just as a physics question, but as something larger, because the darkness seemed like a simple thing. It seemed like the kind of thing you explain to children in 5 seconds. Oh, it's dark because there's no light. And then, if you actually ask carefully, slowly, following every thread, you end up at the cosmological constant problem, you end up at Hawking radiation, you end up at the 95% of the universe that is invisible, you end up at the quantum vacuum, you end up at the edge of time. And that journey from the familiar to the profound, from the simple question to the abyss, that is what I think science is, not a collection of facts, not a textbook, a method of following curiosity until you fall off the edge of what anyone knows. And here's the thing, the darkness was never empty. We were We were the ones with the limited detectors, the narrow eyes, the tidy assumptions. The universe has been full this whole time. We've been walking through a universe packed to the brim with things we can't see, calling the parts we can't see nothing, and being impressed by the 5%. And that's not a failure of the universe. That's an invitation. That's the universe holding out its hand saying, you haven't even started. You think this tiny visible sliver is everything. Come see, come follow the thread. Come ask the stupid, obvious question that everyone else already thinks is answered. Because the next time you look at the dark, and whether it's the dark of a room or the dark between stars or the dark of the vacuum or the 95% that constitutes most of what exists, the next time you look at the dark, I want you to remember this. You are not looking at the absence of something. You are looking at something you don't yet have the instruments to see, and somewhere right now a young person with enough curiosity and enough stubbornness is building those instruments, or will be, or could be. If only someone told them that darkness is not the end of the story, that the dark is where the story actually begins. Go on, look into it. I dare you.